I hope everyone can see the screen here. Right. Okay. So, a very warm welcome to all of you who have tuned in today. So we are very excited to introduce this compute architecture with the RISC-V course that we have actually been planning since 2023, if I'm correct. This is mainly put together by Abba, who will be speaking today to all of you. Without further ado, let's dive into the information session that we have prepared for all of you.
Aba again.
Please mute your mics, everyone. So, wait. Okay. Um, okay. So today's agenda will be covering the following. Um, we will be having a keynote speech by Dr. Ajith Pasqual, who is one of the leaders in this field of computer architecture in Sri Lanka. And he'll be talking about his journey as well as um, one of the key companies in this field in Sri Lanka, Parakum. Um, then we'll be moving on to a brief history of chip design by Abarajithan. And the next session will be a modern day compute architecture design overview by Kaveesha. And then I will be covering sort of um, a background into open source ASIC design and like the opportunities available to all of you in this area, including kind of a custom silicon demo of a 32-bit RISC-V processor. And once we've covered all of that, we'll be going into the course logistics and the future opportunities available in the IC design domain. So that will be covered by Dr. Subodha, who will be joining us from, I think, Scotland. Um, yeah, and then we'll have a small Q&A session if anyone has any questions. So let's welcome Dr. Ajith Pasqual. A bit of background about Sir. He's the current director of the enterprise at the University of Monato, and he's promoting innovation and entrepreneurship through the university currently. And he was the former president of the Sri Lanka Electronics Manufacturers and Exporters Association. He's the founder and CEO of Parakum Technologies, as I mentioned earlier, and he was the former head of the department and a current senior lecturer at the Department of Electronics and Telecommunication. I'd like to welcome Sir to give us all a brief background and an inspiration about the passion about like learning this field and current opportunities available in the country and as well as overseas. So, yeah, stage is yours.
Thank you, Kithmin, for the introduction. Can I share my screen?
Yes, sir, of course.
Yeah. Just give me 1 minute. Hope the slides are visible to you. Hello.
Yes, we can see this.
Yes. Once again, good evening to everyone. Thank you, Kithmin, for the invitation. So this will be fairly a high level, like presentation on what computer architecture is basically in RISC-V, pretty much actually kind of journey within the department, and some of the projects related to RISC-V that we have actually been doing for the last almost like a decade. So let me jump into saying that, okay, so this is we are in the kind of right time to doing the computer architecture. This is I want to start with this. Those who have been following my lectures probably have seen this before. So this is a Turing lecture done by John Hennessy and David Patterson. Those who are not aware of these two guys, they are the inventors of the modern day RISC architecture back in 1980s, or I can't remember the exact time. So they were awarded the Turing Award. They got the Turing Award in 2018, and during the 2018 Turing lecture, they mentioned the golden age, a new golden age for the computer architecture. Now, this is basically somewhat actually surprising when you look at from the history of computer architecture, which dates back to say 1940s, probably even before that. From stored one-in-one architecture, like when stored program computing actually was introduced initially. And since then, the actual, I would say, the kind of not necessarily rapid growth as such, but from 1980s onwards, we saw like fairly fast-paced development in computer architecture. But those all the theories that we learn today, pretty much 90% of the theories that we learn today are 40 years old. Okay, so in what context are we talking about a golden age? So this is sounds bit of conflicting, but I mean there's a lot of like insights into that statement that's the golden age. So unlike, for example, like machine learning, where you see, I don't know, 100 papers coming every day, probably. You don't see that many papers actually computer architecture. It's slow growth, but it's forming the base of hardware. That machine learning on GPU might be a different story, but still a lot of things are based on general CPUs. So want to start with this statement just to highlight and just to basically to give you a bit of a push to say that okay, what you're studying actually is not in waste, and it's actually the right time to study this and get into this computer architecture and basically try to innovate as much as possible. When certain, I mean, that type of innovation actually was kind of inhibited like sometimes back, which I will come to that in a little while. So as you all know, like when you talk about computing, is the computer is I mean, essentially a data processing system, right? We are processing data, all type of data, and to process that data, we need instructions. And so those instruction set architecture, what we call instruction set architecture, is pretty much the base set of instructions that would help us to do certain things, to actually do many things. And these languages or these instructions are obviously developed identifying what the requirements of a general computers are, whether it's a general purpose or application specific. And all those like instructions that we see are again, I mean, nothing new as such. This idea of ISAs, as I just mentioned, probably more than 75 years old, and I'm sure that everybody actually has heard of these pretty much well-known ISAs. x86 is from Intel, and 8664 is also from Intel, and AMD 64 from AMD, and then ARM, MIPS, Power, that's from IBM, and Spark is no longer there from Sun Microsystems, now actually part of basically or was an Oracle processor, if I'm not mistaken. So these are very well-known ISAs that has been in the market, maybe sometimes pretty much, let's say, one cannot say dead as such, but still actually being used in certain cases. But what has actually spurred the growth of why do people actually start saying this is a golden age is on one side, even though these ISAs are well known and publicly available, everybody has access to this ISA. If you go to these vendors, manufacturers like Intel, AMD, or all these other players, if you try to actually try to develop a processor based on one of these ISAs, you take x86 or AMD 64 or maybe MIPS or PowerPC from IBM, I mean, you will get sued next day, because even though it is open, they are proprietary. They are owned by the relevant companies. So even though this ISA is widely available, I mean, you cannot actually use it for your own development as such, maybe just for academic purposes. But even so, academic, you cannot develop a processor and basically put it into a paper or research paper saying that, okay, I have developed x86 equivalent a processor as such. And Intel can definitely actually sue you if you do that. So all these things change all of a sudden in 2010. Starting from 2010, and then in 2-3 years around that time, RISC-V from University of Berkeley was introduced as a public domain ISA specification. It's very important. It's a public domain ISA specification. It's just a specification of what ISA is all about, with all the instructions, formats, and everything actually is there. And that changed the game, because that is something that you can pick. And then you can develop a processor, and nobody actually would be bothered about suing you as such, because it is widely available and no one actually is claiming ownership of that as such. And that allows widespread, I would say, interest all over the world to basically develop processors on their own. And for example, if you look at India and China, India has their own processor called Shakti from IIT Madras. And Madras or Bombay, I can't remember exactly, but I think IIT Madras, they have their own processor, and they have declared their Shakti as their kind of national processor. They use it for their own critical infrastructure. Like, for example, maybe their space program and their nuclear facilities and maybe defense applications. They use their own processor, pretty much getting free from, or basically freeing from the traditional processors that have been used to. So that's a kind of independence, okay? Independence or freedom from freedom, what you would like to do. And even though the well-known ISAs that I mentioned, pretty much all of them came from US. And so the urge to basically come up with your own processor is not just with the likes of basically from India and China, but even in Europe. Europe basically Brno is basically a very close ally of US, but they are actually pursuing their own architectures, to become independent of whatever the current set, like from Intel, AMD, and all that. So having something on your own is something for them is like national security. When you say national security, is basically European security. Similarly, it's the same for China, for India as well. So this is actually created now. Looking back, those who have actually running the country, running the USA right now, say open or basically making it public specification is the biggest mistake that they have done. Okay, but anyway, that has already happened, so we can actually make use of that opportunity. So that this is something that we ought to keep in mind. And a little bit of ISA. ISA is as I said, language of the computer, and it sits between hardware and software. Okay, and it's like a house plan, which everybody can understand. The architect can understand, you can understand, your building contractors can understand, pretty much everybody can understand. And that's the language that everyone understands, and simply shows what the capabilities of the processor is, what sort of capabilities that you want to actually have. If it is a general purpose processor, or if it is custom one or specific one, you will say, okay, I need only this type of from instructions. That's what actually ISA is. And you give that ISA, and anybody can actually develop or realize that ISA using hardware, which we call actually microarchitecture. So ISA covers pretty much. I mean, see a lot of. I think during this course, I think you will be all taught about these things, like memory, data address bus with data types, instructions, internal number of registers that you require, ALU capabilities, all form part of the ISA, the instruction set architecture. And microarchitecture is a realization of that ISA in hardware. And the beauty of that actually is for a single ISA, there can be so many different realization of microarchitecture, like the same ISA, to meet different expectations. Like it could be performance related, or it could be energy efficiency, or it could be silicon area, or resource if resource constrained environment, you might actually want to have something very resource efficient. So all depend on your end objective. Where do I actually want my processor to run? Like, is it IoT application? Is it something like I want to run on a data center? Or is it something that I want to run on a very low power, like embedded type of device, which in a single battery charge, I want to run it for 10 years or something like that. Okay. Depending on all that, you can customize. You can customize the microarchitecture to meet that end goal. So the very basic idea is microarchitecture is all about basically like two paths, like what you call a data path and control path. The data path is where data is going all over the place. How do you interconnect the registers, ALU, memory, buses, all of them? And the control path is what really controls that data movement, okay, from one place to another place. Basically, every instruction will go through step-by-step process of achieving the end objective of that instruction. And who controls that? That's the control path. And the controller of the CPU is what actually generates these control signals. So this is very briefly, very high-level view of what ISA is and what microarchitecture is, which you will be definitely learning in much more greater detail during this course. So having said that, let me, because this is more like a high-level overview, let me just quickly dive into a little bit of history of RISC-V at our own department at Electronics and Telecommunication Engineering. So what you see is a bit of history. I think I might have missed actually one or two, but I think I can't also remember exactly. I think I started teaching RISC-V probably 2015, 16, or a little bit before that. But the first project actually was started by, in fact, two projects with batch 2012. I'm not sure that anyone actually is here from that batch. RISC-V base ISA processor. RISC-V actually is, I think probably again you will learn, it's a modular ISA, means like there's a base one, which is with very, very minimal set of instructions, but sufficient to do a lot of things. And then you have a lot of extensions, okay, which you can actually add those extensions to increase the functionality of your processor. One extension is, for example, like integer multiplication division, a very simple one, but without that also actually you might be able to run certain things. So the base processor development actually was started as a final project back in 2016 using Verilog. And same year, another group actually focused on low power RISC-V processor for IoT applications. And that was just a preliminary, very basic thing that we started in 2016. And then second time, we started in 2017, batch 2013, again a RISC-V processor, in-order processor with not base ISA plus, like integer multiplication division, and I think atomic instructions also, and direct map cache, and again using Verilog. And this was a very passionate group. Again, I'm not really sure whether anyone is in the audience. And what they did was, I think one guy joined from another group also, who was not actually doing RISC-V earlier, and they managed to work in their after hours while they're working and managed to boot Linux. And that was a major achievement, back in, I think, 2000, maybe 17, 18, around that time. And they managed to boot Linux and to show that your own processor can be developed and boot operating system. And that was I think is a kind of a moment that everybody wants to remember. And third one started. I think there was another project in between also, but then it started in 2022 or 23, batch 2018. I think I saw Kaveesha in the group, so he was in the group, and a single core out of order processor. But the development actually was done using Chisel, not using Verilog as such. And then batch 2020, I think some of the resource persons are from that batch, that group, extended that project to multi-core cache coherent processor. and got it actually working. And still, probably we had to do a little bit of more to things get to working fully boot Linux as such. So quickly going through that one, I think I have limited time. This is just like a snapshot of the architecture that was used in the 2012 group. As you can see, a very basic one. Then 2013 is a bit more advanced with a multi, I think probably 8 stage pipeline with instruction cache and multiple stages in data cache as well, along with the integer multiplication division like unit. So these are some of highlights of that particular group. You can see they were able to achieve 100 megahertz operating frequency on a Cyber, which is a very small Xilinx FPGA, and open design. And they actually this time call more a wing processor, but I think after they got the Linux to boot, they call the processor as Simba processor. But anyway, this was in 2017, around that time, I guess. So this is basically again the resource utilization. And then 2018, we again kind of restarted everything from scratch. It's an out of order single core RISC-V processor using Chisel. So this is again the overall high level architecture. And I think it was running at 65 megahertz on Silent Set board and out of order 185 megahertz and partial Linux boot. And some issues were there, but like this project again continued by the next group, 2020 group. I think some of the resource persons are here, or the batch group students are here. They use the advanced branch predictor called TAGE, like with this tag geometric history length branch predictor, 4 cores, and set associative memory cache coherency is one of the most important addition that they have made, in addition to making it multi-core. And you see basically the resource utilization on a Vertex Ultra-Scale Plus processor. So this is basically a few diagrams just from the architecture, multi-core architecture. As you can see, each core inside actually is given on the right-hand side, upper right-hand side. And basically this is a cache coherent interconnect part. And then L1 data cache, L2 data cache, and the front end, the branch prediction unit actually is also there. So this processor was developed using Chisel, as I mentioned, that's starting 2018 batch. And we still need to make it actually fully boot Linux, and documentation actually still going. And once all these things complete, we will be making this project open source. I think there's a lot to be learned from this project as such. So we want to actually make the documentation like kind of perfect so everybody can learn out of it. And I hope that we can actually do it quickly. So this will be, as I said, open source, hopefully sooner. And so getting back to this course again, what should be our end goal in studying computer architecture? I think the primary goal obviously is to develop your own RISC-V processor. This is hard, not an easy task at all, definitely doable, but it shouldn't be your ultimate goal as such. Because the reason is, just like as I mentioned at the beginning, we had this is a public domain ISA specification, which means that everybody who is interested in hardware might be doing the same thing just like you. So you cannot actually just be satisfied saying that, okay, I have done my own, I got it to work. But what you learn you should be able to actually apply it. And ultimately, it should bring some economic benefit to you as well. Otherwise, it's just for a hobby. A hobby actually will not generate revenue, or a hobby will not actually allow you to survive. So if you really want to make a difference, a difference, it has be a different processor than like ABCD. I mean, your processor should be something different. So how do you make that difference? Now, the how you do that actually is to depending on where you want to target your processor, like whether it's like a high performance processor, whether it's like a IoT like type of processor, or like very low cost, low power type of processor. This three-dimensional design space actually has so much of infinite possibilities, and you can position your anywhere in this 3D space. So that is, I think, the first step. Obviously, the course outcome of here could be just that you are able to realize it in hardware, but that should not be your ultimate goal. The ultimate goal actually is how do you actually make it something that is different from another one, and that should be your ultimate goal, and work towards that. Okay, that's actually one thing that I would really want to highlight. Again, going back to what John Hennessy and David Patterson actually mentioned during the Turing Award, like they say at that time, 2016, not during Turing Award, actually, basically it's sort of email. David Patterson actually say like this is the time for application specific processors, because the general CPU is not meant, or what you call general purpose. Some people argue that it should not call general purpose, but that general CPU is not meant to be addressing, for example, like a high performance or like a low power or maybe a low resource type of area. It's the only way that you can actually meet those targets. If somebody wants high performance, then what should I do? If somebody wants the extremely low power, what should I do? And if somebody wants basically a very low cost, meaning low resource processor, what should we do? So only way that we can actually get this improved energy cost performance is to go for domain-specific co-processors. Like, I mean, you can actually make it depending on the case, having the relevant extensions targeting those specific domain. And this is like basically the Moore's law is ending, not actually dead yet. And Dennard scaling actually has pretty much ended, which means like as you lower the nodes, like the voltage and current also actually drops. But the power density actually was remaining constant. But that was broken, I think, in the beginning of 2000, like maybe around 2005-6 era. So that data scaling actually has pretty much stopped. So with only way that you can actually make it make a processor to target a specific area that I mentioned, performance, power, or area, is to do customization and basically explore the different designs. So this was from a recent conference, like again, a processor company. They say custom compute. So basically what he says is, I just repeat that, the processor industry needs new ways to create differentiated products. And how do you do that? Through architecture optimization, hardware, software co-optimization, and domain-specific acceleration. Okay? Or basically, in other words, custom compute. So you will be learning the basics today. But as I said, like what the future holds is how do you really customize? How do you really customize for different purposes? So just actually getting the basics and laying the foundation with this course, I believe. And how do we differentiate? As I said, these three, and design explorations for each and every module in the processor. I mean, you saw some block diagrams that high-level architecture that I've shown earlier. And each of these modules can be optimized. Okay, can be optimized depending on the parameters can be changed. And all depends on your application. I mean, be thoroughly aware of where your application actually is processed. It's not just for small application, maybe a IoT application that can be probably like can be sold in millions. So if I do that, how do I actually differentiate? And from the front ending part, from instruction fetch, prediction, that area, all the way up to the back end, the full execution part, you can actually do a lot of optimizations. So for that, obviously, like being deeply aware of what these building blocks are is essential for such optimization. It's not something that you can actually do on a surface level. You need to know what these blocks are really doing. I will, since actually Kithmin also actually mentioned Paracom a little bit, so let me also highlight one small example of what architecture optimization means, actually not related to RISC-V, but digital design. So back in 2015, 16 era, around that time, we again, set of graduates from electronics developed this high efficiency video coding video decoder. It was a 4K resolution. 4K resolution is 3840 into 2160 pixel. There's a quad HD resolution. At 60 frames per second decoding on FPGA, and we demonstrated that like for the first time in the world. Okay, and this required a lot of optimization, to run the system at 150 megahertz, and to make sure that actually it fits into the FPGA that we use. I mean, these are some of the resources that are used, and pretty much again a lot of data movement actually is there between the core and the memory, and this data bandwidth or the amount of data transfer actually was reduced by about 70% using a latency aware a cache architecture. So this is just briefly the high-level architecture. I'm not going to actually explain obviously what these different blocks mean, but these are the HEVC architecture and the actual setup that was actually demonstrated like back in 2015, 16 the time frame. So with this, allow me to conclude. Again, reminding this is RISC-V is a public domain ISA specification, so everybody has access to this, and you can actually develop your own processor. Nobody actually will be bothered about it, but don't stop at just getting that knowledge and building something working. But even though it is hard, even that step actually is hard, but many will be doing the same. Okay? So what you really need to do is go beyond that one, and don't just stop at that point, and start design explorations as much as possible by understanding what each and every block actually does. And if you do that, and if you know all the parameters, you can actually change all these parameters to modify your architecture, to modify or customize your architecture to a very specific need that I actually mentioned about performance, resources, or power. That's, I think, conclude this. I think I took a little bit more time, I guess. Sorry about that. I hope this gives you a little bit of insight into what RISC-V is all about. And I wish you all the best for you in following this course and actually making your first RISC-V processor. Thank you very much.
Thank you so much, sir. That was a tremendously inspiring overview that you gave. And thank you for continuing to inspire the future generations as well as all the work that you're doing. With that, I think we can move on to the next session. So I'll invite Abba to share the screen and
thank you, Kithmin. So allow me to please excuse me from
yes,
the
sir.
meeting. Thanks.
Sure, of course. Thank you, sir. Thank you for your time. So Abba will cover the brief history of chip design.
All right. Hello. Yep. Okay. Can you see my screen?
Yeah, good.
Okay, great. All right. So I'm Abba. So I'm a PhD student in UC San Diego, and I was a former intern at Qualcomm and AMD. And I done my undergrad internship at CSIRO in Australia in robotics and AI. And I did my BS in like ENTC in Sri Lanka. So I worked as a junior lecturer and as a consultant and in UOM. Also, like I worked for about 1.5 years as RTL design engineer in a startup from Canada, where I developed some compute cores to accelerate AI inference and training. All right. So today, let's like discuss some parts of like around CPU and like how it has been designed historically. So, and then Kaveesha will talk to you about like what are the modern trends in computer architecture, right? So, all right. Okay. So, first of all, what is a CPU? So now I'm sure like all of you have written some sort of program. So like you have done some programming. So like a program is simply basically just an algorithm, like where you step by step you say what to do, right, on a high level. So and you might have seen charts like that, right? And you write that algorithm into code. So as a C++ code or like maybe Python or like you have different languages. So you write your program into like your code, right? So in compiled languages, what you do is like you then compile this code into this machine code, or like you compile this into assembly, right? So, and when you compile it to assembly, like you actually get a file like this. If you open it and see, and you can use it in, you can view it using this IDEs, right? So you can see the most important part here are the instructions like this. That is push R28, push R29. Okay, so LDS and MOV, stuff like that, right? So this basically now what all these are the instructions that are given to the processor. So the C++ code is a high level language for you, and this is translated into a low level language with what step-by-step instructions to the processor. So basically move stuff from this register to this register, right? So move from R19 to R23, and then you have so push something to the stack, then pop something out of stack, then like call some function. Okay, so and yeah, so all these are like very tiny, like a very basic step-by-step instruction, right? So, and these instructions you have like you move stuff from one register to another register, stuff like this. So this is what the ISA is. So when you say a processor's ISA, so this is like AVR, like any particular ISA. So would be what interface to the programmer, right? Oh, like Dr. Pasqual said, it is sort of the blueprint, or like the blueprint that everyone involved in the programming the processor and building the processor and everything understands. So it is sort of the understanding between the hardware designer, like whoever designs, whoever implements that CPU, okay, and whoever programs that CPU, right? So because they both need to have some sort of a common understanding to build the thing that the other guy wants to use, and he should know how to use that thing, right? So basically, like these are the ISA is basically like a list of instructions that are supported. Okay, so like this move, this is supported, and it will take this many clock cycles, and it will have this side effects, etc. So and then these are the register fire stuff. Okay, this many registers are there, this many general purpose registers are there, and you can basically move like zeroth register might be just zero. Okay, the value zero. So all of these are part of the ISA, right? It is the understanding between the programmer and the designer, hardware designer, right? So yeah, and assembly is basically now whatever the code programmer writes converted into that very basic sets of instruction, right? That is what assembly is. So in this course, you will learn to write assembly, okay, for RISC-V assembly. You will write interesting programs in RISC-V assembly, and then you will like run in your own processor, and you will like see it working, and you will see the internals and stuff. Okay, all right. So the next part would be like assembling. So that is the assembler basically takes all these instructions and converts into ones and zeros. So, and there is this pre-defined like opcodes. So basically, if it is move, it might be some number 11200 something. Okay. So, and this register means it has a particular number. So like all of that becomes these numbers, binary numbers, right? So there is assembly, and that's how you get the machine code, right? So, and then this machine code is like a very big, like a long string of bits, and then you load these bits into your processor. Okay, so here the simplest, let's say IoT applications. So people use AVR processors, and Arduino Uno is one as a processor. Okay, so the Atmega 328P, right? Like there is a processor. So you can see, like you can upload into it, and this is the actual CPU, right? Where things run. So now the CPUs come in all flavors, just like Dr. Pascal mentioned. So from IoT low power applications to high performance, like server class CPUs. Okay, so they're like a huge range. So this is the like on a embedded low power side, right? So, and then you can basically take this CPU out, and you can build your own product. Okay, so like someone can build their own product. So like there is the CPU designers don't do that. So there is that is basically how CPU basically what like gets implemented into real world products, right? So okay, then we have this is a Atmega 328P, and like if you open this up, open up a CPU. So the question is like, how does this CPU actually work? So you have this in computer architecture, you have this the front end side where like you have the actual computer architecture. So where you study branch predictors and like all of that. And then after you design like your architecture, you have to implement it. So that is how that's what Dr. Pasqual mentioned about like you put it on the FPGA, which is like a flexible chip, or else like you can, and once you test it and it works, you can actually make it into your own chip as well, right? Which can be a bit expensive, right? So we will talk about that a bit in today's session as well. So when you make it into your own chip, so this is how the actual Arduino chip is like. If you take the top of the chip off, so like if you take the packaging, like if you remove the packaging, so this is how it looks like. And it has like the die has several layers on top of silicon, and like basically you remove all this. Yeah. So, and after looking at everything, so you can see the design actually looks like this. Okay, so that is the silicon, like when you see from the top, it looks like this, right? So you have like lot of areas, and the components that you see, that branch predictor and all of this, you can identify on a high level from here, right? So okay, this is zooming into a CPU. So the question is like how a CPU is implemented. So like, I mean, how a CPU works on a very low transistor level. So if you take the packaging off, it looks like this. Yeah. And if you zoom in, yeah, so with the scanning electron microscope, you can actually see on a much higher detail. So you can see these are the wires and like the in the different metal layers of the chip. So, and you have actual transistors, like very small transistors, and they are connected to each other on a very tiny level, right? So that is how yeah. So in our course, we will spend some time discussing on how it's implemented and the low level stack and stuff like this as well. So basically, we'll take you through the process of doing this, like building like a chip like this, at least the using open source tools. Okay, so that is also part of our chip of our course. All right. So like, what are these layers? What is in there? Like if you take like a cross section on a side or something, you can actually see stuff like this. So that is on the very bottom, you have these transistors. Okay, so on over here you have the transistors. So that like the transistors sort of look like this. Okay, so like when you have gates, so this is how you like build a small gates, and then layer by layer you connect those transistors by different set of wires. Okay, and you have like global interconnects that span like long distances. So all these are wires, metal wires. Okay, so these are deposited on top of each other step by step, and so it's basically like a very thick, like a sandwich or like a burger, right? You have like multiple layers of stuff, right? Where you have yeah, so that is what a chip is, right? So all right, so this is the machinery inside the processor. So like this is a very popular processor, MOS 6502. So it's used in Apple 1 and Apple 2. So there is this visual simulation on how this thing works. So let me see if I can say that. Yeah. Okay. So can okay. Okay. So can you? Yeah. I guess you can see it. So now this, what you have here are the instructions. Okay. So, and yeah, so these are the instructions, and this is the CPU. So, and like you can, okay. So you can see this, the instructions actually executing. Okay. So which lines are being activated. Okay. So this is an actual, like a very popular CPU from like the 70s, right? So what you see switching are the, like you have the actual transistors, and they control the current flow in these wires, right? So on the sides you have all the like where you send the data, like the IO pins. Okay, all right. So this is pretty interesting. And over here you have the like yeah, so the register values and everything, right? So okay. Right. So yeah, yeah. So this was is the process that was used in Apple One and Apple Two, okay, and Atari and Nintendo, like these gaming consoles. So it was a like a really popular processor back then. Okay. So how was these processors like sort of built and implemented? So what is the history? Like what is the story of them? So in the 50 years ago, in the good old days, okay. So this is like a calculator. So, and it was the Busicom, this one, it was like it was a Japanese company, and they wanted basically some sort of a like so they had circuits, of course, and they have chips back then, but then they didn't have something like a processor, right? So then what they hired Intel to like build something, okay, so which you can put it on this, used to program these things. Okay. So and so this guy, Federico Fagin, so he was hired by Intel to like continue this project. Okay. So he got in, and then he designed the very first CPU, right? So previously it was like, I mean, you are not actually programming stuff. You have just like bunch of circuits, and the circuits do the same things again and again, stuff like that. So you can't program them to do like different things, right? So the the CPU like he designed was like this. So this is the original schematic. So the idea is like the computer architecture on this side, that is what like this course is about. And that is what Dr. Pascal talked about as well. So you have the control path, and then you have the data path. So like you have the ALU is the arithmetic logic unit, where you do multiplication, addition, and all of that. And then you have a bunch of you have stack and you have registers. Okay. So you store data into the register, read it out of the registers. So this is from 70s, right? So this is the 4004, the very first CPU's architecture, right? So you can see it is very similar to modern, like in the sense on a very high level, the same things are like in today's CPUs. Okay. The only thing is they are like so complex and so optimized to like squeeze out like every little drop of performance, okay, out of them. So this is like the simplest like sort of the design, right? And then because it was the first CPU and like the very early days, so you don't have any like very logo, you don't have anything to design stuff. So like you basically have to do the entire ASIC flow, the chip design flow by hand, right? Like manually. So this is the schematic they came up with, right? So the original schematic. Yeah. So in this schematic, you can see all the different transistors and but yeah. So basically how the transistors are connected and stuff. So basically he had to convert like whatever his architecture was into an actual schematic connecting an electrical diagram, okay, by himself, and to implement it. And then, yeah. So another question is, how do you actually get that thing working? So for that, as I showed earlier, you need to have transistors. So, and you have to have transistors in silicon. So then you have to draw this layout. Okay. So basically, this is the layout, okay, of the first chip. So you have to draw this layout by hand. Okay, how to connect these wires, how do you lay these transistors, stuff like that. Okay. So, and you have to make sure like that works. So that is the hard part, right? So, and after all this, okay. So this is how they actually made it. So they had to draw things by hand and then like cut things. So, and like this called Ruby cutting, where you cut the like a different layer. So you see all different colors here, the green, red, and blue, and all of that. So these are the different layers of that sandwich. So for every layer, you have to make a mask. So that is, you have to make something that is only that layer. So what you do is you can use that mask to like etch like the metals and everything like in every layer, right? So it's a photolithography process. So this is what they and you have to cut these every layer like this, and again they had to do it by hand, right? And after doing everything, so this is what they like finally got the first version of processor. So it's 51 years ago in the 1971, right? So 10 micrometers was the node, and then you have 2000 other transistors. So and it ran at 740 kilohertz, okay, like doing like 92,000 instructions per second. So there is a simulator actually, like you can go there and like play with the simulator and you can see that. Okay. So this is the board of the DCCOM. So and inside that you had like four of these. So you had like two of these 401 RAMs, and then the ROM, and you have one CPU over here. Okay. And you have like a bunch of other stuff, and all of these are connected, right? So yeah, and this is the actual packaging you can see in this corner. So it's a packaging. Right. So this is sort of like a high-level overview. You can see the decode is happening here, the ALU part is here, and the register banks, it's stacked. So all of these are here. Okay. So yeah. All right. So the thing is like, but that was a long time ago. So that is like 10 micrometers, right? Like 50 years ago. And today we are at like 4 nanometers or even 2 nanometers right now, right? So, and there's work going on in the more advanced nodes as well. So, what does this mean? So, like, how is this, like, what is going on here? So, every year, so people have been having like smaller and smaller nodes, okay, from 90, 65, all these nanometers up to 4 nanometers. And how is this possible? So, the thing is like, what now the thing, like, things are way more complex. So, if 4004 was a house, like today, the CPUs are as big as a country, right, to put things to scale. So like that is 4.1 million times bigger in terms of transistors, right? So every year, new chip and millions are being sold, right? So which means more or less every year you have to release a new architecture, new chip design. So you have to do all these things. So how can people build something as big as a country like every year and make sure the whole thing works? So especially millions of them, like in different people's houses, hands, and everything, right? So it's a miracle, right? So that we are able to do this at this scale, right? So the miracle like is possible because of abstraction. So abstraction means like you have like a lot of layers in this process of how do you do this process. So and in this different layers, nobody knows everything, right? So the computer architecture guy doesn't know like everything about like physical design or putting stuff and everything, and the guy who like actually like works with the physical design tools don't know much about computer architecture. So like basically you have like multiple levels of layers, and then you have common standards and everything where you can send like and you can reuse parts, okay, between those layers, and you can, yeah. So this is what makes it possible, right? So you have cat tools which are smart enough to optimize high level logic, but they are like very expensive because they have to be very accurate. Otherwise, the company loses millions of dollars, right? So, and then you have industry standards like System Verilog GDS2, which makes this possible, right? So here you see the number of transistors have been doubling every 2 years. So that is the Moore's law. So the number of transistors have been growing exponentially, okay, in the chip that is doubling every 2 years. So and there is a Moore's law. Yeah. So with every shrinking, you have like denser, faster, and more power efficient processors, right? So, but then, so you have this like the people say that Moore's law is dying. Okay. So, which means like we can't, hello? Yeah. So
We can
we
hear you.
can't, yeah. So we can't just go on forever because like industry need like we have gone to the point physical limit of a transistor. So like we might hit it like pretty soon. So that is you can't make it smaller than a atom or two wide, right? So there is a physical limit. You can't just keep going. So which means like at some point Moore's law has to stop, and the transistors will become like won't get smaller anymore. So which means you won't get like the power efficiency and the density and the speed and everything that comes from Moore's law. You can't get it after that. So which means the industry needs better designers right now. Okay. So they have been coming up with like new architectures, okay, all the time. So yeah, and these are the modern chips. So you have the M1 Pro, which is like did a massive revolution, the MacBook chip, right? So in so like you can see, and even before that you had Intel Core i7 processors, i9 processors, all the laptop chips. So you have see all of these are like multiple multi-core designs with performance cores and this efficiency cores, right? So you have like yeah, so, and they shut down some of the cores in different times to save power. So these are all computer architecture, very high level concepts, and which work closely with the low level problems, right? So there is like with the power and like transistors and like how do you implement these things and stuff like that, right? So yeah, and then you have this like iPhone processor and yeah, all right. So you have all these different processes, and the CPUs are not just used in your machines. So they are also used everywhere. So like they have used in electronic systems, in networking, like in your infotainment, in your like TVs, in car displays, basically all over the place, right? So yeah. So basically these are used. So there's like a massive. This is a massive field, right? So yeah, so with this, I hand it over to Kaveesha to like discuss the modern day computer architecture design. Right.
Yeah, hi. Uh,
Yeah,
Kithmin, can you share?
yeah. I will. Sorry, I will share the screen. Okay. Yeah, you can see the screen, right, Kush?
Yeah, okay.
Great. Okay. Yeah, so you can introduce yourself. Go ahead. Thank you.
Yeah, so like the slide says, I'm currently an electronic engineer. So I'm working as an engineering consultant to a agency which is in the US, and I was previously design verification engineer for Sci-Fi, which is also a chip design company. So we ran tests to like test the chips design and ran some tests. I got my BSc from Electronic and Telecom Engineering from University of Marola. I was also, like Dr. Pasqual previously said, I was one of the parties. I was in one of the groups that did a processor in 2022. We can move on to the next slide. Yeah. So these things also mentioned by the previous speakers as well. So the challenges in modern computer design comes from mainly the end of Moore's law, which means we can't keep putting more and more transistors into the chip. There's a trade-off here, so it's not, we can't infinitely put them in there. We are reaching a physical limit. End of Jenner scaling, that means we actually need more power to power these extra transistors and security. So this is kind of new. Like previously, we assumed that hackers only exploit a software code, Now hackers have started exploiting hardware as well. Recently, in one speech, someone said they have also started exploiting physics as well. That's more into RAM. We can go on to the next slide. So when it comes to manufacturing, we still need it. Like that's why you see if you are watching the tech news, like every single company is trying to get TSMC. Even though the progress isn't there compared to most slow, it's still we are still adding it. And one thing you have to know is that the chip design is a multi-year endeavor. You can't exactly, okay, now we finished the chip, where can we manufacture it? We have to think of that before we are starting the chip. So it's important that those things move on. You should be aware of what's happening there in the manufacturing as well. One of the most famous examples was the Intel 11 generation, which was scheduled to be processed in another node, which wasn't there at that time. Like the timeline didn't match up with the fab, so they had to do an old process manufacturing, which completely destroyed that product line, the high performance ones. So we need to be aware of manufacturing as well. Wait, I can move on. Next slide. So one of the downsides of going into those most expensive nodes is that they have a little bit of higher defect rate. So chips come in this wafer. You have see on the bottom right hand side. Like the smaller nodes have higher defects. And when you decrease the chip size, you kind of increase the yield. How many valid chips that you can use. On the right hand side, you can see that when the chip size reduces, you can increase the yield as well. So AMD pioneered this with the Ryzen chips. You can see that on the left hand side, you have the Intel 9900K, which is like one monolithic chip. It's one big chip with everything inside. And on the right hand side, you can see the Ryzen chip, which has three small chips. And the bottom chip is actually IO. And that IO chip is made in a less expensive node. So you can actually reduce the cost as well through this method. So people are rethinking of ways trying to mitigate the problems that we had. We can move to the next slide. And so this is kind of big. So if you look at your computers inside your motherboards, you can see that the CPU is one thing and the RAM is another thing. There's a problem there. So RAM is a little bit far away. To reduce the latency, current chip designers are trying to put everything on the chip itself. So we can see on the M1 block, those two RAM chips are right there with the chip. So it's not just these guys. So Intel is also doing it with their new stuff as well. And another thing is that what I'm trying to say is that people are rethinking of what the computer is. We are rethinking it. We are trying to redefine the computer, how components are placed there. So it's not just about looking at the pipeline. You need to be aware of what's happening, because without these improvements, whatever the improvement that you're doing in the CPU pipeline will not show any benefits. Yeah, we can go on to the next slide. And inside these computers as well, it's not just the CPU anymore. We have other chips as well, other, let's say, computers as well. If you see that the CPU, you have the CPU and we have the GPU. Everyone knows the GPU and we have the MPU. Those kind of accelerators, we call them. They are there to accelerate specific tasks that the CPU is too slow to do. It can still do it because it's general purpose. But we are giving those other accelerators the job to do it faster. But they can't do what the CPU does. The CPU is still needed. And actually, with all these things, communication between them is becoming a huge issue now. So yeah, we are trying to find solutions to that as well. We can go to the next slide. So before moving on to the next part, I just have to give you a quick introduction to the CPU pipeline. Each instruction goes through this fetch, decode, execute, memory access, and write back stuff. So since we need to increase the amount of instructions that we are handling at a time, we break this into 5 stages. so that we can run 5 instructions at a time. So one instruction will be fetching, one will be decoding, one will be executing, one will be doing the memory access, and one is in the write back stage. So instead of doing one instruction at a time, we are trying to do 5. We can go to the next slide. And even with this, we have a few issues. So fetching takes a long time because we have to like access and remember that the RAM is a little bit far away. So we have to go there and fetch it. So it takes a little bit of time. And we don't really know what the next instruction is to fetch it. So if you think of, if you've done programming, you have written if statements. And like without knowing what the value of the if statement is, we don't know where to go in the program. So like that, we don't know the next instruction always. And execution also, we don't know what the, like some instructions can be done quickly, like addition, subtraction. Some take a little bit more time. One of the famous examples is like division takes like a very long time. And if you like need to like see a good example of this, search query algorithm, the fast inverse, I believe fast inverse something. So in that, instead of using like logarithms and stuff, they do it very quickly using very fast instructions, which massively improve the game. And also memory access, again, we have to go to the RAM, it takes a long time. Now we can go to the next instruction. So next slide. So to mitigate some of the problems, we have a thing called cache. So we try to predict what we need, before we actually need it. So we predict them and we fetch them and we keep it close to the CPU pipeline. And we call that area a cache. And we have a lot of predictors to predict what we need and put them there. And next one. Next slide. So, and another thing is that the different instructions take in different time. While we are waiting for like a divide, we actually try to do other additions as well. So kind of like, so this is out of order execution. And another thing is like, since we are having all these transistors, can we put more than one instruction at a time to each of these pipeline stages? So what we call superscalar. So like trying to figure out all this, like trying to figure out answers to all these problems, the final pipeline will look something like, can you go to the next slide? So the final pipeline will look something like this. So with all these transistors, we are trying to put more execution units. You can see here that you have something called ALU, intmal, branch, AGU, like all those things are execution units. We try to have more cache. Actually, the cache is like a very big part of the core. If you like go to the previous slides and see, the cache takes up a huge space. And higher clock frequencies, smarter predictors, deeper pipelines. So you can see here is not just more, there's more than 5 stages here. And wider decoders and schedules, like we are trying to feed more instructions, like having more instructions at a time. Yeah, we can go to the next slide. So with all these things, we actually try to put as much as performance as possible. Like in the history, there were like they theorized some attacks when we are doing all this stuff. But the thing is, like we never, the hardware designers never thought that they would be practical. So in 2000, I can't remember, it was after I think 2012, maybe 2017, I can't remember. Google actually made a practical attack. I think it was Google. They did a practical attack that actually shook the designers a little bit. And there was like a huge problem with it. So like some of the processors had to be like slowed down massively to mitigate these threats. So there are like even more hardware problems as well. Like so there's this thing called row hammer that attacks the RAM. So like there are more and more threats there. So yeah, we need like more designs in terms of security as well. So yeah, there's like a lot of stuff happening right now in the computer architecture side. It's a little bit interesting. So yeah, hope you like enjoy the course and want to proceed a little bit further. Yeah, thanks, Kithmin. Yeah, Kithmin the next.
Oh yeah, okay. So yeah, let me just Thank you, Kaveesha. So I think Kaveesha covered the area of modern computer architecture design. So let me reshare my screen. I'll actually move into a different window. Um, okay. So you can see my screen, right? Okay, right. So I want to cover this section here. So I'm going to sort of do a small demo of a project uh, all of you can actually do if you take part in this course. All the resources are available to sort of do this. Like we have gone through all the workflows and the resources required for this kind of project. Oh yeah, a bit of background about me. So I finished my master's in electrical and computer engineering from UBC last year, and I'm currently working in the sort of the semiconductor sensors field here in Canada. Um, and I have some experience in like analog IC design and silicon photonics and that area of it. But yeah, most of my expertise is not currently in the digital design domain, but I'm planning to contribute most of my knowledge gained in open source IC design to this course. So this is the demo that we want to sort of go through today. So I have this board with me. Um, this is the tiny tape out um, 6 demo board. It has this processor here, or processor like it's actually a ASIC designed with custom silicon projects. So this is the chip that I'm talking about. This exact chip has been fabricated and put on this board here. And the nice thing is we can access all of these projects on this board. I can actually show you the board. Let's see if I can get the yeah, I don't know if it's working. Isn't it? I don't know why it's blurred actually. Oh, I think I know. Okay. Um, okay, yeah. So I think you can see the board that I connected. So it's connected to via USB to my PC, and there's a Q mod connection here externally. So this is the board that I'm using for this demo today. We can do the rest without the PC. So the idea here is to actually use this project that's on this board. So this wasn't designed by me, but this is exactly something that this course is focused on. This person has designed a 32-bit processor using RISC-V, and he has sort of designed it in a way to be able to boot Linux. I think most of you probably know what that is. And I've also connected a kind of external EMOD device here. This thing. So it has like SPI flash and two external RAMs that allow me to sort of, I think, hold the image of the OS, the Linux OS that I'm planning to boot in the this processor. So it's a very exciting project. I also don't fully understand all of how it works, but I'll by the end of the course I'll probably have everything understood. So here's the USPI flasher. So I've already programmed the um, image onto the board. This is the command interface with the processor. So here, what we've basically done is we have connected there's a UART console or UART module on the processor. So we've connected the serial interface here to that UART module, and we're like able to communicate with the processor now. And since the image is already on the external USPI, it's basically going to like communicate with that and load Linux. So this is kind of the workflow that's happening here. And at the end, like once it's done, it took like 2 minutes to get here. And once it's done, it came up with this interface. And like if you are familiar with Linux, it's like a small, like right now, this is a basic operating system, and it interacts with the standard commands that we use to, like I can go inside one of these folders, maybe use it. So right now I'm communicating with a custom design that's on a custom chip that was like fully designed. This is the project. So this is like entirely designed by a person. Let's see. Yeah. So this is the entire project that he has made, and like we are actually communicating with the OS that he programmed onto his project. So this is it's pretty cool, I think, if you think about it. Yeah, above, feel free to comment if you have any things to add here. Yeah, but like this is the demo of this, and we'll share more resources about this as we go on to the course further. And I have some slides about open source design, so I'll quickly cover it in like 2 minutes, and I'll be handing it over to Dr. Subodha to cover the course introduction. So, okay. So, in this course, we're going to talk about the open source IC design flow, and open lane is kind of the like the foundational structure, like the design flow that they have introduced for open source PDKs. So this is kind of an overview of that. If you guys took our previous system Verilog course, I think most of you are familiar with this. And these are kind of the PDKs that we'll be working with. There's a PDK from IHP and the like the great, so like the old older version of the PDK that was used in the open source community is the Sky 130 PDK. So we'll sort of be using one of these two PDKs to do a project. And this is a kind of a idea about the previous projects that we did using open source silicon. So some of these are analog projects, but like we've done this matrix vector multiplier project. Abba actually did this tape out, and then we've also done a RISC-V processor tape out as well. So all of this was doable because of the time tape out platform. So I've added links for you guys to go through and find information about this, and we'll also share more information during the course. And then this nice project or competition was held last month. This is the crowdsourced RISC-V peripherals project, and they have some very nice designs and implementations. You can go to this link and read about most of these projects, but as far as digital design goes, most of these projects are very interesting, and we'll be getting the PCB or the demo board with these projects next day, so we can actually try a few of these ourselves as well. And this is the project we did. It's an analog project, but this is just to show that in Sri Lanka we are developing the capabilities for open source silicon designs. So I mean, in the analog side, it's going pretty well, and I'm mostly contributing to the analog developments, and this course and future courses in digital side will also help us get more progress in the digital design side of things as well. Yeah, final outcome, as Abba mentioned, we're into making new chips and chip design development. So all these courses are to progress that field in Sri Lanka. So Dr. Subodha will talk more about that. With that, I'd like to hand over the next part to Dr. Subodha to cover the course introduction. Yes, I think
Kithmin, I
Dr.
hope I'm
Subodha. Yeah, we can hear you.
perfect. I started sharing the screen as well. If at any point it goes away or if you cannot hear me, please let me know.
Okay. I think the screen. Oh, wait. Let me see. We can't see your screen yet.
Zoom says that I'm screen sharing.
Let me see. Maybe can you try again? Just stop sharing and.
Okay, stopped.
Okay, now we're good. Yeah.
No, it's fine.
Yeah.
Okay.
Thank you.
Right. Thanks, Kithmin. Yeah, I'll quickly build on top of what the previous speakers were talking about, giving you an intro about what you will cover in this course and a few housekeeping items as well, and then what you need to do if you are to enroll in the course and move forward with us. A quick intro. I'm currently a senior lecturer at the Department of Electronic and Telecom, University of Moratuwa. Graduated from the same department and then completed my PhD at the University of Florida in the US. My research area was mainly on-chip security when it comes to multi-core architectures. What we will cover in this course is a continuation of a few things that we did in the past. I'll give a bit of background. When we look at the Sri Lankan economy in general, we can talk about our service sector, but what we are trying to do is to do capacity building in some high value areas. We need to develop a knowledge economy if we are to be competitive in terms of giving skills, whether we are having companies like Synopsys or any other multinationals in Sri Lanka. For a company at that scale to come to Sri Lanka and establish their presence, we need to show that we have the critical mass. We need to show that we have skilled engineers within the country who can do these things. Because whenever a new company is looking at a country to establish their presence, what they will look at is, does that country have a skilled workforce who can cater to the requirements, right? So in terms of chip design, we noticed that we have a very low output. People from the Department of Electronic and Telecom, we get 100 students every year. But even within that 100, people specialize in different areas. Some people do machine learning. Some people will go into things like electronic circuit design. Among all these things, the number of people specializing in chip design is very low. Kaveesha talked to you earlier. Kithmin, Abba, we are all products from the same department. But we need more people to be experts in this area. So with that motivation, about 5 years ago, Abba initially developed a course that was his passion. That was 2020. But later on, we built on top of that initial foundation to give a more structured set of courses. What you see on the screen is that what we started was course number 2, the System Verilog for ASIC FPGA Design and Simulation. You can see the outline of that course here. We started by developing very simple digital circuits. Throughout the course, we developed several, as you can see on the screen, and we taught you the theory, we taught you the tools and techniques by designing these digital systems. Then at the end of that course, what we realized was that for someone to be able to take this course and then be proficient, they need some background knowledge. So in the second iteration, last year, we developed a more basic level course, Fundamentals of Digital System Design. So that's what you see here in this flowchart. We started by number 2, realized that it might be too complex for a few people, and then we went back and did course number 1. So Fundamentals of Digital System Design covered even more basic concepts like finite state machines, even before that, combinational and sequential logic. And then we slowly moved our way forward towards developing the digital systems that we taught in course number 2. So at this point, we have completed course 1 and course 2, and that brings us to course 3, which is what we are talking about today. So the continuation of these 3 courses is such that at the end of course number 3, you would have built like a very simple processor. We originally envisioned that to be a combination of the digital circuits that you built in course number 2. We are, of course, taking a few components from here, but we are introducing a lot of new concepts in course number 3. So where are we headed? Once you complete all these things for the first time in Sri Lanka, what we wanted to do is for you to be able to tape out your own chip. This is where we are headed. And those who have at least a small understanding in this domain, you know that developing or taping out your own chip can be very expensive. It's not a $100 exercise. It's a $1 million exercise. But recently, that has been made a little bit more cost effective by some of the players in the market. Like, so we've worked with Tiny Tape Out and now Chip Foundry. You can see some of the partners here on the screen. What they do is they make some of these resources available on top of an existing fabrication process. Right? So we have these shared mechanisms where some of the space are shared, and that makes it more cost effective. Having said that, now that cost comes down to the range of say $100, $200, right? But in these courses, you will see the cost of the course entirely is less than $100, $200. The reason is we've had the generous support of several partners, like Synopsys is one of the sponsors that we had for the previous courses. They've given their tools free of charge. Otherwise, if we had to pay for it, it'll be very expensive. And we've also had grants from organizations like IEEE, which are partially funding these tape outs, right? So that's why we are able to give it to you so that even if you are a student, at a very affordable rate. So these are a big picture, starting from the very basics, go all the way to the point of taping out your own chip. And you are currently here in this path. To give you a bit more details about course number 3, which is our main focus, it will be taught to you over several weeks. You can see the structure here, the weekly curriculum, the topics that we are covering. And we plan on meeting on Saturdays and Sundays. And we'll also have what we call the office hours. Once you enroll in the course, you will get more details. So I'll not go through like the exact timing and all that. You can, of course, refer to the slides. We have a hybrid setup where we record the lectures. So even if you miss like a class, you can go back and watch the recording. However, please don't take the recording as an excuse to not come to class. The reason is, if you come to the class, then you can ask questions. If you get a doubt, you can resolve it right then and there, rather than waiting for a week. We encourage you to learn this material together with the instructors live, because that is the most effective way of learning these things. We'll also have some recorded content available to you, so you can refer them and then come to class. So we'll have a mix of different methods of delivering the course content. So what will you learn? Everything that you learn will be centered around this particular course project. So the course project is to develop a single cycle CPU using RISC-V. So what we'll do is we'll start with something very simple, something very basic, and then iteratively we'll improve it. Because as many things in engineering, you first have to get it working. And once you get it working, you try to optimize. So we'll follow the same. We'll iteratively implement a CPU. We'll add new instructions. We'll make it complex step by step. And then finally, we will talk about concepts like multi-cycle. We'll talk about branch predictions, and then some advanced concepts in computer architecture. If you have ever followed a computer architecture course in university, you will see concepts like pipelining, and within that pipeline, hazards, how do you manage them, branch predictions, um, out of order execution. All these concepts will be taught to you. However, when designing these courses, one thing that we absolutely wanted to emphasize is the starting from the very basics, and while you build it, slowly moving towards those more advanced concepts. Because you can definitely understand those concepts. That's not very difficult. But understanding something and then applying something in a real world design are two different things, right? You first need to understand and then apply. That is our traditional method. But in these courses, we have flipped it, meaning that you will learn things that will allow you to build these things, these designs, and the complexity of it will increase iteratively, gradually. And once you do that, you will also build or apply what you learned in class. So that way, it's not like a whole bunch of advanced concepts you learn and then you come back and you try to implement it. That is not the case. You will start from something very simple, build the design together with us, and then the complexity will increase very slowly, right? So the reason for taking that approach is, like I said earlier, we started 5 years ago, especially thanks to Abba, who talked to you earlier. And we've received feedback and we've iteratively refined the course. Similar to you iteratively learning these concepts, we've also designed the course iteratively based on feedback. And now we are in a really good place. So we know what works, what doesn't, and that way we can deliver like a very good learning experience for you. So this is the course project, and this course project is broken down into content across different weeks. So day 2 and 3, you can see we start with something simple as a state machine, and then we convert that state machine into a CPU, and then we develop the first, simplest, useful, because what you build initially might not be useful, but we want to convert that into something that you can actually use. That will happen in days 7, 8, and 9. Excuse me. Sorry, I got a little cough, so I had to mute myself. Right. Okay. Wanted to get some water. Please excuse me again. Sorry about that. Hope it's settled. Okay, so once we pass the initial simple useful RISC-V CPU, then we'll understand what kind of instructions can you run on this CPU. Well, in fact, those two things about like designing it and the instructions will go hand in hand. So we'll walk through those things, especially looking at the RISC-V assembly, understanding how those instructions are executed in our processor pipeline. We'll cover them in these days. So once we have that working, we have a end-to-end processor working, even though it's simple, then towards the end of the course, we will talk about multi-cycle CPU, what is pipelining, and then some advanced topics. How do you measure the performance of a CPU? Things like Amdahl's law, and then branch prediction. I'm sure you have heard of branches. If you've ever done like a Python or C programming language, you've had if-else statements. So when you execute those statements in a processor, it's a branch, meaning that if you're taking the if statement or the else statement, or in a switch, in a case statement, multiple options, in the processor, the behavior now has to be captured, right? And to speed things up, we have things like branch prediction, where we try to predict, are we taking the if path or the else path? So concepts like that will be used to optimize the performance of your processor. So those things will come towards the end. But in the first few days, we'll start from scratch, from the finite state machine, from the state diagrams, and then we'll get something working end to end. So that will be the structure of the course, and we'll conclude by leaving space for future courses. We'll talk about things like system on chip, and that will be like a good segue for any future courses that we are building on top of this basic foundation. So now if you're thinking, in that first diagram I showed you, we had courses 1, 2, and 3. Kithmin, please correct me if I'm wrong, but those who are taking this course, but you have not taken the previous courses, we will make that material available to you. So any gaps in knowledge that you have, is that accurate, Kithmin?
Yeah, we can make that available. I think Abha is also doing a primer on system Verilog in this course as well.
Perfect. Right. So you'll get like a 1-day quick summary about the concepts that we covered. But if you're interested in referring back to the previous modules, that can be made available as well. Right. So you can see on the screen, what is the target audience? Who is this for? I think that's pretty straightforward. And these are the feedback from the previous courses that I told you earlier. And in fact, the reason why we keep going, we've not only done computer architecture courses, we've done some electronic circuit design kind of courses as well. Some of you in the call, you might have been a part of that. The reason why we keep going is that we've received some good feedback and also some very constructive feedback. And upon those constructive feedback, we have refined the courses. You can see some of those on the screen. And the thing that encourages us the most is the learning methodology of actually building something rather than you listening to a whole bunch of lectures. That building part is really resonating with the audience, with the students. That way, I'm sure you've heard of these teaching methods where you listen to something versus you apply something. These are two different things, right? That way you internalize some of these concepts in a much better way. So we've seen that good feedback throughout the courses that we have offered. You can see some of those things on the screen as well. So compared to the previous iteration of the course, I told you about the complexity, the gradual increase of complexity. In addition to that, we are also exploring some open source tools and the tiny tape out, the actual chip tape out that I told you. So those are things that are new in this iteration. So I encourage all of you to go through this. I hope that gave you like a very brief idea. And if you decide to enroll in the course, you can go through those topics in much more detail. Once you enroll, for you to be able to complete the course, or for us to consider you as passing the course, we don't have grades, but you need to complete the assignments, at least 3 out of the 4 assignments. Otherwise, you will not be eligible for the certificate that is issued by the University of Moratuwa. We also have quizzes. You need to complete them. You can have any number of attempts to complete the quizzes. So we are not grading you. You are not getting an A or a B or anything like that. We simply want you to learn these concepts. That's all. So if you get a low mark, you do not pass the quiz in the first attempt, try again. And you can refer the content again and then come back and attempt the quiz. Because if University of Moratuwa is certifying that you have this knowledge, we need to be sure that you have this knowledge, but it will not be like a traditional class where you write a paper and you get a grade. Not the case. You have unlimited attempts to complete them. And we also recently had the Microelectronics Olympiad. If you're planning to face that next year, this can be a good place to learn some of these concepts as well. So I think this year's competition is in Armenia. We also developed a competition, like a local, like a Sri Lankan competition, to select the winner. That was again in collaboration with Synopsys. We selected, I think, a few, and then one person or 1 or 2 people went to the international competition. Right. So we are developing this whole pipeline of you learning these things, going to competitions, actually taping out the chips. That's the ecosystem we want to build. So the students get like a really good exposure and they'll be ready for employment in these areas. That's our long-term objective. So this is the team that will be delivering the course material to you. Some of these team members you met today who spoke. The others you will meet in the lectures, in the office hours. So please get the best that you can get out of these individuals. Everybody who's worked in this domain for a long time, so they have first-hand experience and hands-on experience. So like I mentioned earlier, it's designed to be outcome-oriented. We teach the fundamentals with real-world applications. And this is the first time we're offering this course number 3. So we've custom-made everything. And like you saw in the previous slide, it's taught by a highly qualified panel of people. A few remarks before we wrap up. Kithmin, Abba, or anybody else in the course team, please feel free to jump in and add anything if I missed. The course will be conducted in English mainly, but if you have a language barrier, you don't understand some of the terms, Sinhala and Tamil explanations will be given. So we'll have Sinhala speaking and Tamil speaking lecturers. So if there's anything you want to ask, you can ask in a language that is comfortable for you. So we'll be more than happy to explain. We also have time allocated every day for question and answers, and then during office hours as well. This is an example of the certificate that you will be getting, but the wording here, you can see it's Artificial Intelligence in Embedded Systems. That is a sample. It's a certificate that we gave for another course, but you will get something similar with details specific to this particular course. What can you do with what you learned? I'm not going to go through this. I think we emphasized the motivation behind these courses. That itself should give you some idea. I would just highlight one thing. Many people, I don't know whether you have seen this, but in LinkedIn, there's been like images circulating around that is showing the number of people getting placements in the software industry, like the traditional web stack. There's nothing wrong with it. We need people who have expertise in there. What we are trying to do is to give another option to those who are interested in a different domain. When you look at it, it's also coding. It can be interpreted as software, but you need a deep understanding of how hardware works and how these instructions work to be able to go into this particular software phase. So it's not software in the traditional sense, but it's still coding. And given that it's a very niche area, it's a supply and demand thing, right? If you have a lot of engineers being trained in the web technologies, front end, back end, DevOps kind of technologies, if the demand is less, it will be challenging for you to find job placements. But when you are an expert in a domain that not many people are experts in, you have bargaining power. And for you to have bargaining power, you need to be very proficient in these areas. And there's also this misconception that these kind of hardware languages are difficult. Well, that is not the case. We just have resistance because we have a way of like sequential thinking in traditional programming, but we need to change that slightly, and then you will be able to master these things. So just get rid of any preconceived notions that you have. Just be open-minded and dive curiously into these domains, and I guarantee you that will be like a very rewarding and fulfilling experience if you are willing to put in the time. Because if you enroll and you don't come to any classes, you don't actively take part, well, you might not get it 100%. So actively take part, ask questions, and then you will be a person who is very much in demand. Kaveesha talked about being being a consultant working for countries outside of Sri Lanka. That's a trend. Well, one good thing out of that came out of COVID, among many bad things, is that. So make the best use out of it. If you are a proficient person, then you will get opportunities in Sri Lanka and outside of Sri Lanka. And in some cases, you will go, in some cases, you will stay here and work remotely for a company that is doing chip design. Either way works, but it's pretty rewarding, because the problem that we had earlier is that some people complain that there is no industry. Where do we apply? Well, now there is. So, and they are demanding more people. So it can be a positive cycle where more companies come here, given that we have critical mass of talent to show. So that's what we are doing, right? So if you decide to take the course, the next step for you by 19th of October is to fill this form. You can go to this link over here, follow the instructions. There's a payment to be made, and then complete the form with all the requested details. Please make sure you follow the instructions, because sometimes, just to give you one example, we have explicitly said do not deposit money through ATMs. Those are the automated machines. Why? Because you cannot add a reference number. And the reference number, if I'm not mistaken, even here will be your NIC. So that is the way that we can identify that, okay, it's you who made the payment, because we submit all the payment details to the university finance department. So for them to be able to recognize that you have actually made the payment, we need those reference numbers. So those instructions are there. We've had students earlier who said that, oh, I used an ATM machine because it was faster. We understand. You can also do like an online transfer. But if you go to an ATM machine, we have no way of recognizing you, because the reference number is generated automatically. You cannot add a number. Maybe some newer versions do. But my point is, just go through the instructions carefully and make sure you follow them. So if for you to be able to complete the course, you must complete the evaluation criteria. I showed that before, 3 out of 4 assignments. Attendance will not be taken, but please don't use that as an excuse. We can of course say that attendance is compulsory, right? But what if you have like a personal commitment or a work commitment that prevented you legitimately from coming to class? So we want you to be able to refer to something and then complete the course, but please don't complete the course entirely online. That will not be the ideal learning experience. Those who enroll will also create a WhatsApp group, and you will get all the details there. So if you have any questions, I think now is the time to get them clarified. I'll post here anything that you want to ask from either myself or from the previous lecturers who spoke before me. Anything you want to ask, please feel free.
You can send your questions through the chat. Okay, there's a question. Abba, maybe you can take the first part of that. Abba, are you there? So the course fee is mentioned on the flyer, and it will also be emailed to those who registered. I'll just share the link to the flyer here. So, oh, sorry. Yeah. So just go through the flyer that we shared for this course. You can find the course fee at the bottom. I will also be emailing the instructions next week. Okay, I think Abba is not available, so I'll record this feedback from Udara to send it to the team. Any other questions? Please get your questions clarified today, and then we'll also be sending out the emails next week. And then you can join day 2 after you have decided whether you want to enroll or not. Yeah, looks like everyone is okay. I think we can conclude the session, Dr. Subodha.
Sure. Yeah, so I think we've had around 45 to 50 people joining today, so it's really nice to see. And hope the enthusiasm will continue. We hope to see from day 2 onwards. Like I said, please make sure that if you're enrolling, that you are here for the entire course, get the best out of it. Like I said, the motivation is to train people, right? So we hope you are equally enthusiastic about taking the course and learning. And so we welcome you to be a part of that journey of learning together. So thank you. Details here. Check it out. One last reminder, the deadline is 19th October. Kithmin and the team will keep you informed for those who already registered. So thanks for being here today. We look forward to having you in the next sessions as well. Thanks.
Thank you, everyone. See you in 2 weeks. Thank you, Dr. Subodha.